Hello everyone, welcome to my channel. Let's learn computer science. Okay, today we are going to learn about BCD, binary coded decimal. Syllabus reference show understanding of different number systems. Under that, this is mentioned here, binary coded decimal, right? So, if we look at past papers, then questions they come that convert binary uh, coded decimal into denary, or a denary number is given and you have to figure out the equivalent binary coded decimal, right? So today we are going to uh, look at what BCD is, how BCD addition is done, some past paper questions, and plus application areas of BCD and hexadecimal. That's our today's session, what we are going to learn about. So BCD, let's start with what BCD is. So BCD is basically binary coded decimal, and it is just another method where you group bits into bytes. Okay, so you have some numbers and they are grouped together in the form of a byte. Now, in BCD, we have only single digit denary numbers that we can represent using BCD from 0 to 9. We only have equivalent values for 0 to 9, nothing beyond 9. We do not have any value. So only single digit denary numbers, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, they can be represented using BCD. And a nibble is what? A group of 4 bits. So nibble is used to store a single denary digit. So 0 having an equivalent. So I have made this table here. So 0, one nibble is 4 zeros, which is equivalent BCD code for decimal number 0. Then 1, 4, 3 zeros and 1, 2, 0, 0, 1, 0. This is a normal conversion table that I told you about this in when you started learning about number system, right? So these, starting from 0 going up to 9, we have equivalent BCD codes. We do not have any equivalent code for 10, 11, 12, or anything beyond that. So this is a table that will be handy during the conversion questions. So you always write this table on a blank page, or on a rough sheet while solving question papers, past papers, right? There are two ways to represent BCD, right? uh, Normally in your questions you'll be doing it using packed BCD, second way. However, there are two ways: using one BCD digit per byte or using two BCD digits per byte. So what is the meaning of this? So when we say each BCD digit has its it is used to represent any denary number using 4 bits. So when we say that using first method, when we say using one BCD digit per byte, that means 4 equivalent bits are going to be wasted, because one denary number has one nibble, right? So rest of the 4 bits will be filled with zeros. How? I'll show you with the help of an example down there. But before that, there is another method using 2 BCD digits per byte. So if we have 8 and 9, we have to represent it. So you'll write 1000 and then you'll write 1001 in one byte. So half of half byte, this will be filled with, half byte next digit will be filled with. Let's see with the help of an example. So let's say if the question is write 305 using BCD representation. So first of all, what you will do is you'll figure out the equivalent BCD values for individual digits. So for 3, 3's equivalent BCD digit is 0011. 0's equivalent is 4 zeros. 5's equivalent BCD code is 0101, right? Now, using first method 305 can be represented as 3 will be written using 1 byte, right? First 4 bits will be filled with 0. Next 4 bits will be filled with equivalent of 3. Second byte, first 4 bits will be filled with zeros. Next 4 bytes will be filled with equivalent of 0. Then one more byte will be used to represent 5, where first 4 bits will be filled with 0, and next 4 bits will be equivalent of 5. This is using first method, using one BCD digit per byte. However, there is another method using 2 BCD digits per byte. So as per this method, 305 can be represented as for 3, we are writing 0011, and whatever is left, we'll fill it with zeros, because we do not have 4 digits here, we have only 3. So along with 3, we have to fill 4 zeros. However, next 2 values, they will be written using 1 byte, where first 4 bytes are for 0, and next 4 bytes are for not bytes, sorry, bits. Next 4 bits are for 5. Yeah, so that's how it is done. Next, we have BCD addition. It is not specifically mentioned in your syllabus. However, this is there in one of the reference books, so I have mentioned it here. BCD addition. Now, if we look at okay. Now, if we look at these numbers, 0.74 and 0.89, these are decimal numbers, right? If we add them, the answer that you get in denary is 1.63, right? Now, however, if I convert 0.74 and 0.89 in BCD and then I add, we get results which are, not expected. So let me just show you. Okay, so this number 0.74, its equivalent in BCD is, for 0 I have written this, and for 74, this is 7 and this is 4, right? Similarly, for 0.89, this is for 0, this is for 8, and this is for 9, right? Individual digits, their BCD codes are written. Now, if I add this, I get this. However, if I add this and this, I get this. 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1. But this is incorrect. For this, equivalent binary is this. But result that I got after converting this into BCD and then adding, this is incorrect result. So what is the solution? Why is this incorrect? This is incorrect because these values are not acceptable in BCD, right? In BCD, we do not have any equivalent for 15, but this value is 15 and this value is 13. So we do not have any value beyond 0 to 9. Only single digits can be represented using BCD. However, these values are not represented in BCD. That is why we are getting incorrect result. Now, how to fix it? Let's see. Now, what we do, we have a correction bit. As a solution, we have a correction bit. Whenever we get result above 9, which is 1001, then we add a correction bit 6 in denary, and binary in binary it is 0110. So we add a correction bit to the result. So how? Let's just see. So this was our value 0111 0100. From here I have taken this. This will take it in the end. Firstly, we'll add this and this. Okay, so this and this, when we add this, so we get this answer. However, as I said, we do not have any equivalent in BCD for 15 and 13. So this is 15, this is 13, and we do not have any equivalent. So what we do, we add a correction bit. So correction bit is 6, which is 0110. So we add this, and whatever result we get, if we have a carry bit, we'll add this carry bit to the next value, right? Now, because next value is also incorrect, it is 15 and it is not acceptable in BCD, so we will add, again we'll add a correction bit to this value, plus we will add carry bit to that. So this, I have written it here. So this plus correction bit plus 1 from here, this carry bit, I'm adding it here. So this number, because this is 15, which is not acceptable, so I'm adding a correction bit, plus I'm adding a carry bit, which is from here, and answer is this. Now this number, of course this number is acceptable, however there is a carry bit again, right? So this carry bit will be added to next of the zeros, right? So final answer that I get is this, which is correct, which is equal to 1.63. Right? So that is how we do BCD addition, right? Now there are few past paper questions. Let's have a look. So first question is from October-November 2022, 961811 paper component. So question is, convert the BCD into denary. So this number is given. So we have to convert it into denary. Very simple question. So what we do? We just take first nibble. We look for its equivalent in the table, conversion table that we created here. So we look for the equivalent here, and then next bit, next nibble, and we look for the equivalent value here, and we write. So this is 7, right? This is 7 and this is 2. So 27 is the answer. You get full marks if you write the correct answer. Then next question is from November 2022, 961812. Here they have written, convert the unsigned. Unsigned means number is positive. There is no sign associated with it. Unsigned binary integer. Now binary integer is given and you have to convert it into binary coded decimal. So binary is given and binary you have to convert, right? Now this is binary number. You know how to convert binary to denary. So you will convert this into denary first. So we'll add all the place values of all the bits where 1 is written. So for this one, place value is 128. For this one, place value is 16. For this one, place value is 4. For this one, place value is 1. We add all these place values and we get 149. So 149 is denary number. Now we'll figure out equivalent BCD for 149. How? We'll look for one equivalent code for 1, for 4, and for 9. So equivalent code for 1 is 0001. For 4 is 0100, and for 9 is 1001. So one byte will hold 49, another byte will hold 1, and rest of the bits will fill with zeros. So final answer is this. Right? Easy. Now, next. Next question is from May-June 2022, 961813. So question is, denary number 87 is given and you have to figure out binary coded decimal. Very easy. Figure out code for 8, individual code for 8, and then individual code for 7. So 8 is 1000, 7 is 0111. You write it together and that's your answer. You get full marks if you write it this way, right? All right, now, last but not least, we'll look at application areas of BCD and hexadecimal. Syllabus reference, describe practical applications where BCD and hexadecimal are used. Very simple question, and you get 1 or 2 marker question based on this topic. So question is, describe application areas of BCD and hexadecimal number system. So firstly, we'll look at hexadecimal Okay. Firstly, we'll look at firstly, we'll look at BCD application areas. So display screen of calculator, you must have used, digital calculators. So there, the digits 0, 1, 2, 3, 4, 5, 6, 8, 6, 7, 8, 9, they are written using BCD coding system. So that is an application area for BCD. Another one, digital clocks. There also time is displayed. That is done using BCD. Currency values display. That is also an application area of BCD. Now, uh, hexadecimal application area of hexadecimal. So for hexadecimal, you must have seen these uh, color codes, RGB color codes, FF0011. That is an application of hexadecimal number system. Error codes, 404 error. Error codes are in websites, error codes that you see. That is also hexadecimal application. Memory dumps, then IP addresses, then MAC addresses. All these are application areas of hexadecimal, right? So that's all for today. Today we have learned about application areas of BCD and hexadecimal, and we have learned about what BCD coding system is, how to convert a denary number into BCD, binary coded decimal, how to represent a BCD code. Then we also looked at BCD addition, how to correct it when it is given in decimals, and there were some past paper questions that we solved today, right? So that's all today. Thank you.